Hello, this is a video walkthrough for assignment 5 in course 330 parallel distributed programming in my UNE IT Graduate Diploma course. This program is a implementation of the Gaussian blur using MPI with actually mine is not a tree topology, it's a star topology. I'll explain why later. I'll insert the link there. Basically, this program is the purpose is it takes a bitmap image and applies Gaussian blur in parallel fashion. Alright, so first I'm just going to do a make clean and remake the file, and then I'll just maybe run a demo first. I'll just delete this first two just so I can redo it again. Okay. So if I run, so it's MPI run number process, and I use for process for this one. Gaussian MPI, the name of the program, the name input file pencils.bmp. BMP is the input file, name of the output file. So let's say I want to blur this to 4. I'll limit 4.bmp, and 4 as for the derivative, like the higher the number at the end is, the more blur the image get. So let's try that. You can see it's completed successfully here. We try we can try one more, and let's call this one blur 8, which is like double. Try 8. Takes a little bit more time, as you can see, because it takes more. So you can see it's really blur, but like you see, this one is blur and this one is much more blur. So and also it works on the large, like on the pencil large BMP image, the bitmap image, but it takes really long time. It takes like really long time. So instead I have run the program and blur a large image previous to this prior to this recording, just to save time, and just this image that show it. All right, so let's run through the program, shall we? Where's my Gaussian MPI? Okay. Did I delete it? Oh man. Oh yeah, sorry. I got it back. For some reason I deleted it. Oh, anyway, I got it back. So alright, so my program use a star topology to set up. So let's just start with the main process. So you got the rank, the number process, and you do message passing interface com rank to get the rank of the process you are in, and the com size to get the number of processes, and then separation if we are in a master process, which is process 0, then we run the master process method, or else if we're in the worker process, which is like from process 1 to process n-1, n being number of processes, then we do the worker process. So yes, that's pretty straightforward. So what's the master process? It's reading input image and creating Gaussian kernel. It's distributing image strips and kernel to worker processes. It's processing that's not process. It's on. So I got this challenge before where I got it wrong. I processed some image in the worker in a master process, but I realized that was not ideal. Like I should not do that. So instead, work master process will just distribute all the work to the worker process, and the worker process will do all the work. So after that, it collecting results from workers and writing final output image. All right, so we got our BMP file here. And you got the library, Gaussian library from the lecture, which include all the all the blurring, convolution functions. So we've got a clock time to benchmark performance. So first you check arc, we pass the deviation, which is the number at the end there. You can see the last number, whether 4, 8, how much you want to blur the image by. The kernel dimensions, origin, and then after that you allocate the memories for the kernel, right? And you for I within kernel dimensions, you allocate memory for each of them in a kernel. After that, we generate the Gaussian kernel using this function, which I believe I put it in Gaussian library. Yeah, so you can see here we got the generate the Gaussian kernel. We calculate each term for the Gaussians, and we run the kernel. So that's how you did clone mask, and that's kernel. So let's go back to that. This optional, so I guess it's not needed in here. I was trying to do it for just visually looking, but it got too complicated, so let's not worry about that. Read input image. So we read input image from the BMP file, get the width, get the height, and then create a new BMP file which is identical in width and height and dimension, right? And then you start the clock. So if the number of processes is only one, which is we only have one process, then the master process will do all the work, because obviously there's no worker process. So run the apply convolution. So we're going to look at this function later as well, is the convolution algorithm. Or else, then you got the number of workers will be number of process minus 1, being minus the master master process himself. And then we calculate the distribution parameters. So rows per worker is height divided by number of workers, and extra row will be modulus, so whatever remaining. And then in the Gaussian library, you got a image strip. Hold on, I define the Gaussian library.h. So you got a struct image strip, and it includes all the data of the element you want to send. So you bundle it all in one data type, one structure. All right, so where we at? Sorry, Gaussian MPI. Here we go. So so we gotta know the current row. It starts 0. So where's the next worker start? And then you look through the number of workers, and for each of them, you set the strips width and height, and then work out how many rows for this worker. And if this is a little algorithm, so if the worker number is less than the number of extra rows, then you assign 1 for each. So you go through each one, say 5 workers, you assign divide equally between 5 workers, and then you come back. If there's 3 more rows that need to be assigned, you assign 1 for worker 1, 1 for worker 2, 1 for worker 2, 3. So that's why you got it evenly. And then after that, we add overlap regions for kernel calculation as well, and send. So after that, you send kernel and strip assignments to all worker process. So look through all the process, do use an MPI send, send all the data, kernel dimension, the kernel info, color marks, and then we send the kernel data as well, and you send image dimension, and send pre-calculate the strip assignment. After that, so after all that done, we collect the result from each worker in a loop as well, and you end the clock, and then you calculate the time to see the performance. After that, we save result, write to a new file, create a new BMP file, and we free up the current allocated memory, free up the kernel itself. Okay, so that's the master process. The worker process function is receive kernel and image strip from master, apply convolution to assign image strip, send result back to master. So that's what it does. We got an MPI receive. You receive all the tag kernel info, all the kernel data, all the dimensions of the image, and then you receive the strip image strip struct with all the image data in it there, and then we work out the actual end row with the overlap top and bottom, and then you got the strip height, and then receive pixel data using MPI receive as well. We create a temporary BMPs for processings, populate input strip with received data, set pixel RPG, run the convolution algorithm. After that, we extract results and send back to master by MPI send, and you free up all the memory and free up the kernel as well. So you can see down here all the calculate image strip, document, and distribute image strip and collect result. So apply convolution, I believe, is in here. Yeah, so it's in GaussianLib.c, where is this you apply, you change the pixel, in every neighbor pixel, the kernel, you change it, right? And then that's how you do the convolution. So the key design is to highlight is at first I thought about tree topology, but that means you have to send master to some process, and that some processes send another, keep sending data to another remaining some worker processes, and then all back to master. So I started off, and it gets like messy quick, and I can't work out like the evenly distribution as well as the correct flow of the whole process. So at the end, as I was running out time, I reverted back to the traditional star method, where the master just send the work to all the worker compute all the work, and then send the results back to the master. So I'm happy to settle for that for now. At least the program works for now. So yeah, I just have to go with that. Horizontal strip partitioning. So the image is divided into horizontal bands for parallel processings. You see that in action when we divided the horizontal rows for each worker. There's an overlap region handling. The workers will receive extra rows to handle edges pixel correctly. So if they handle row 2 to 5, for example, they still need to receive, the extra rows on top and bottom to be able to apply the convolution for the edge rows. Load balancings, wherever extra rows is left is also distributed evenly at the start again to each worker process when image height isn't like fully divisible by worker count. So we did that. I guess that's really it. Let me see if I missed anything. I think I'm probably run out of time already. But yeah, that's the main thing. The communication pattern is a star one, master distribute, worker commute, master process. Yeah. What else? Um, Sorry, maybe I just take 1 minute here to think of anything else. Ah, for performance, it should speed up with more processes add. Um, but if you when we don't run the pencil large image, actually more process slow it down because you got more computation required. So for the pencil large, I actually use maybe only 2 process or 3 process, and then also low deviation for the blur. So yeah, that's it for my walkthrough. As you can see here, when you run it, you, you got this print off to let you know what's going on. So the master image division, all the worker process at work, collecting result, and it add like how long do we take to complete the task and whether it's successfully or not. All right, so I think that's it. Thanks for listening, and yeah, that's me out. Thanks. Bye.